start a review session next week. So we won't have a homework due next week. We do have a new homework assignment out. So if you want to get started on that, I think you know everything that you need to know to be able to do the homework assignment. Things are a little bit more complicated, where I give you examples like this one, but I give you more data points. The problem's no harder as long as you write down the likelihood correctly. And if you're figuring out which normal distribution you have, you look at the quadratic term, you invert it. You look at the -2 linear term, you multiply it by that inversion term, and you get your mean out of it. So you're following the same steps. I give you another problem that relates to regression. It's exactly the same. So the mechanics are exactly the same. It's the same problem in disguise, except everything's in vector matrix form. And so that shouldn't mess you up too much. You're looking for quadratic terms. Of course, in matrix or vector format, your quadratic terms look like something with a transpose next to it, where you're pre and post multiplying. Your -2 linear terms look the same as before, but you need to make sure you're multiplying in the correct orders. So you're going to get an answer like x transpose x inverse x transpose y, and if you ended up coming up with an answer like x transpose y times x transpose x inverse, you'll notice that the dimensionality doesn't match. And so you can't do that. And so you want to make sure when you're writing something down with matrices, you're following the rules of the math. And you know what it all means. We can go over all of that in review sessions. So some of you might still be catching up with kind of the foundations of everything that we're doing, shaking off all the cobwebs. And if you want to get together and go through some of those problems next Tuesday, it'd be a good time. Our homework is scheduled to be due the Wednesday following, we'll have another Tuesday and then the Wednesday following that. So about 2 weeks for the homework. So we will have 2 review sessions before the homework's due. But I would encourage you, if you are stuck with things like transformations, ask the question about it during review session. So in these off weeks where we don't have a homework assignment due, you should take that time to catch up. So I don't mean to lecture you on all of this. I just know how all students are. But I remember being 1 day ahead and 1 day behind were totally different experiences. So getting ahead is the name of the game. It only gets more complicated. Again, it's all the same stuff, but there's a certain amount of memorization. What are these distributions? What are they used for? And so that just takes time so that you can embed all that stuff. Anyway, review session next Wednesday, seats 331, 5:30, and then we'll do another one the week after as well. We have a Slack page with a channel on there, and what I prefer is you to write down some of your questions. If you don't know how to formulate the question or something like that, give it a try, and we'll work it out during review session. But it would be a good idea if I could see all of your questions at least like 15 minutes before, so I could think about how to answer all the questions together. It's a big pile. Sometimes some of you ask the same question in 4 different ways. And so addressing it all at once and untangling that can be useful. Again, this is just for you. So you will make of it what you want to do. I don't come in with pre-designed lectures. So if there's no questions, it'll be a short review session. And I hope that at least it lasts an hour. Okay. We're right in the middle of this conversation where we're trying to learn about the precision parameters. So I kind of flipped everything literally and moved from variance to precision. But it's just a one-to-one transformation. I'll remind you that sigma squared is positive, so phi is positive, so this is a one-to-one transform. So if anybody's ever asked you to think about variance, you would say, oh, it's the average squared deviation from the mean. And like to describe that physically, you wouldn't be very good at doing it. So it's this metric. It's a measure of distance from the mean, a measure of dispersion, but I can also come up with a million other measures that measure things distance from the mean. So sometimes that's fairly arbitrary, using that squared error norm. Sometimes it makes a lot of sense. So if you're working with a normal distribution or things that were normally distributed, it makes tons of sense, because if you think about the exponent in a normal distribution, it's all measuring things in a quadratic sense. And so when we get into decision theory, we'll be more formal about this, but a lot of times it's an arbitrary decision to talk about the variance. You could talk about something else. But if you're willing to talk about the variance, you could easily just move and talk about the precision as well, inverting that then. I don't think it's easier to think about the precision or the variance one way or the other. What I think is easier is that we can just think about standard distribution and not the inverse distributions. So this is just going to be done for convenience. In a different country, if you were familiar with inverse distributions or something like that, you might be working with those, and it would be just as arbitrary, and you have to map back and forth. So I will tell you that while around here we usually talk about gamma distributions, if we were in the UK back in the 60s doing this, they would be working with inverse chi-squared distributions. So it's a little bit different. They have to rescale as well. And you can come up with, that's equivalent to a gamma distribution if you invert it. So there's all these one-to-one connections, and it's fairly arbitrary what we do. We'll stick with what you usually see in JASA or JRSS these days. So most people do, but don't be surprised if you're reading the literature and you go, why is somebody using an inverse chi-squared distribution on sigma squared? And you would think it's exactly the same as me using a gamma distribution on the precision without rescaling it. And so if you know your probability theory and all the connections between distributions, you're in good shape. If you're familiar with what those are, but you're not familiar with all of them, you're also in good shape, because if you go to Casella and Berger, there's a nice table in the back that shows you all the relationships between distributions. If you don't like books, there's Wikipedia. And they have pictures and diagrams like that, and they usually tell you connections to other distributions. So just as a very easy exercise, every time we see a distribution, go look it up on Wiki and read about it for a minute. And so doing that sooner will be a lot more valuable than doing it later. Okay. So a lot of this class is just recognizing things and knowing the right tricks. Okay, last time we made this statement, that this was the scale invariant prior for phi. And we also showed equivalently pi sigma squared is going to be proportional to 1 over sigma squared. These are one-to-one transformations of each other, and we did that transform. So we did that transform, and we showed that it showed up like that. And if you were so insistent and you wanted to do a similar transformation and map over to sigma, you would find out that the implied prior that has the exact same information is 1 over sigma if you place the parameter on sigma, not sigma squared. So I'm thinking of sigma squared as a variable, not as an operator on sigma. And it's kind of interesting, they all come in those ratios. And that has something to do with scale invariance. And so nothing changed. We ended up motivating scale invariance like this. So we said we were going to place a prior on log phi that was flat. And so if you just think about a normal distribution, if I write down this thing, f of x1 given phi and mu, that's going to be equal to 1 over 2 pi. Parameterizing it in terms of phi, that's the phi upstairs, I have to square root it. Normally there would be a sigma down here or sigma squared inside of the square root. E to the minus phi over 2 x1 minus mu. And so what we notice is that phi is multiplying by x1. And so if I take a logarithm of that, it turns it into a shift parameter on the log scale. So just a reminder, x1 times phi, logarithm of that, is equal to log of x1. So we would have to transform the distribution of x1 to talk about this. Does anybody know what distribution log x1 follows? So her rule said log normal, so she took the bait. And all of us were about to say that. So can anybody correct us on what a log normal is? It's e to the x. So a log normal is what happens if you take the log of it, it's normal. So it's actually the backwards transformation. It's easy to forget these things. The naming is totally inconsistent. Anybody know what an inverse normal is? It is not the inverse of a normal or what happens if you took the inverse to a normal. It solves an inverse problem that's related to Brownian motion, so the time to reach something. So it solves an inverse problem. So the naming, you can't always just follow it and think that it's an algo. Yeah. So I don't know what. That's something different. We might call these e-normals or something like that. Log phi. So what I'm thinking about is on a log scale, the precision parameter or the scale parameter, however I think about it, gets translated into a shift parameter. And so if we understood what we are doing with mu, then it's sensible to place a flat prior on the log of phi, or log of sigma squared, or log of sigma. It won't change anything. Keep in mind if there's a square out in front of it, it would just pop down if you thought about it as an operator. So if you're thinking about sigma, it's still a shift parameter. So that makes sense. So we had tried to show that that implied this. And really this is just an exercise in doing transformations. Let's do it the backwards direction first. You can always do these in two directions. So maybe this is what you're more familiar with. So if I had this right here, and I'm going to be polite and tell you what that pi refers to. This is proportional to phi. And then I wanted to think about log of phi. And I want to call that something. I'll call it psi, arbitrarily. So that means that phi is equal to e psi. I'll just point out, anytime I write logarithm without addressing it, I always mean the natural log. If you're speaking to computer scientists and they write down the logarithm, they usually mean base 2 because they work in bits. So if you're talking to civil engineers, they work in base 10 because of this. You know, 10 fingers. Does anybody know what a decibel is? Measure sound. What does the unit mean? What log scale is that on? It's a logarithmic scale. It's about multiplying sound. So it means that a 10 increase unit in decibels is equal to 10 on the log scale. So you solve that. So it's like 1.6 something is whatever the log scale that you're working on. And so a doubling in sound is about 3 decibels. Anyway, I don't like the log 10 scale particularly because of all these things. I do like the natural log scale. Anyway, just food for thought. So this is probably the easier choice. Also, if I used a different logarithm, it wouldn't matter because it all just scales by a constant. They're all proportional to each other. Okay, so I've got this. Now I want to transform that. So transform. If you're practiced at this, meaning you're in like a probability class, you can do this in your head. So all I'm going to do is take this thing, anywhere I see phi, and I'm going to plug it in, but I've got to multiply by that Jacobian, which is just the absolute value of the derivative. So in this case, so this is going to be pi psi, that distribution. And so psi is going to be, just remember, that's really just a log of phi. That's my variable name for it. So this is going to be proportional to pi phi, where instead of writing down phi, I'm going to put it in terms of g inverse psi. I'll take the derivative of g inverse psi. There's a lot of ways to do that. So what I'm saying is that this right here is g of phi. That's my transformation. So this is my inverse transformation on the side. That thing you solve for. So that's all we've done. So that's going to be proportional to, again, this was proportional to something when I do these one-to-one transformations. I'm going to move from proportional to proportional. So you might as well just keep this simple. You can't normalize it. So this is going to be 1 over my definition of phi in terms of psi. I get confused too, what letters are which. So that looks like that, times derivative E psi with respect to psi. Like I said, the easiest derivative in the world, we think. So that's 1. So voila, it's flat on the log space. So I could have gone in that direction, or I could go in the other direction as well. So if I wanted to start here, probably some of the difficulty just comes in notation, remembering what psi is. So if I ended up having pi log of this right here, and I said that that was flat, remember what this thing is, it's psi. So again, I use this same exact transformation. Voila. Don't even have to invert this thing. So all I have to do, if I wanted the implied prior on phi, so I write this down. I've got a 1 here, bless you. So that was just pi psi. Psi, that was the 1 right here. And then I need a derivative of logarithm of phi, d phi. So 1 times the derivative of log phi. We're on the natural scale, so we don't have to come up with all those normalizing constants. So that's 1 over phi. So try to accelerate on that. That gives you, if all of a sudden you were thinking about this and the steps are a little bit unsmooth, go back and practice 5 or 6 transform problems. On the new homework, and I guess I'll walk through the homework with you on Monday, there's a transformation problem. And it's just like this, but it's for the beta distribution. So I talk about whether or not people want to place a flat prior on p in the beta binomial example, or if they want to place a flat prior on the log odds. And they're different. They mean different things. So the nice thing is if you weren't careful about this and you didn't really think about what you wanted to inject information on, is we got more and more data, the likelihood it's going to concentrate, get peakier and peakier, and wash out the prior effect. So long as I place positive mass everywhere. The rate in which that happens is, of course, important in any analysis. And so we want that rate to be fast. And it turns out, you're not going to pull, if you use this prior on the scale, this will pull away in the pullback-Leibler sense from the prior as fast as possible. The likelihood will drift, and the posterior will be a statement about your data mostly. But this has some really nice properties. So hopefully that makes some sense. You want to be thinking about in which way do you think about the prior and how do you place mass on it. It's important for a Bayesian. Saying that, if you kind of follow the basic rules that Bayesians have described for you that we'll be carving out in this class, you almost get it right most of the time, but you should stop and think about it. Okay, so we've got our scale invariant prior. So maybe we use our prior 1 over phi, but I want to show you a connection to the conjugate prior. So let's just write down our likelihood function. We've written it right there, but I'll just write it again. So our posterior distribution, given x1 and mu, and what I've said over here is this is the full conditional for phi, meaning that I've conditioned on everything else in the problem. So that's what we mean by the full conditional for a parameter. Everything else is conditioned on all the other parameters. There's only one. If you had a n-dimensional, or let's say a p-dimensional problem, you'd have p minus 1 things over there. So, and the data. So all Bayesian analyses are conditioned on the data. So all Bayesians want the data to speak in a conditional sense. That's important. Usually the notation we'll use later on when we get a lot of parameters in the full conditionals, we just draw a line. And this is pretty standard notation in the literature. So when people are describing their Gibbs samplers, which are based off of full conditionals, we'll study that in a couple weeks. They usually give you this sort of notation and write it all out. Okay. In a moment, we'll study this distribution. So the gamma distribution, that's what we wanted. So I'll write down this. This is going to be the likelihood for phi given x1 mu times our prior distribution. So our likelihood looks like this. And I can get rid of that because I don't want to think through the normalizing constants. So I'm just going to rip off all the constants as I go and just work through the numerator and then recognize it. If you don't know distributions and their properties, this is a hard exercise. If you just look at these tables and read Wikipedia every once in a while, this becomes a trivial exercise. So this likelihood looks like this. Phi to the 1/2, e to the minus 1/2 x1 minus mu. And I'll stay consistent, I'll put that phi upstairs. So that's my likelihood function. And I want to multiply this by our prior, and that will be our posterior. And so if I'm thinking about just our own convenience, and I want to do something that's simple based off of distributions that I already know, you might be running off to the conjugate analysis. So the question is what would this have to be for this to live in the same family? And you can't answer that question until you look at the likelihood and see what it has to multiply against. So by using basic rules in algebra, we understand how exponents multiply and how other things multiply. And so we kind of have to do that exercise in our mind. Of course, I've given you the answer. So this is going to be a distribution in terms of phi. So I need a distribution in terms of phi that I can multiply through that preserves its form. And the key to understanding this is staring at the likelihood and looking at and using your imagination. There won't always be an answer to this. Not all distributions have conjugate priors. So this one looks awfully familiar. Oh, here it is. Now I've changed the random variable just to make this an aside statement. So this is what a gamma looks like in general. The random variable that I'm using is z. So that's just a dummy variable. I haven't done anything with this distribution yet. But gammas look like this. Gammas are always positive. And they're hyperparameters. At least if we are using it as a prior, we call the parameters underlying that distribution hyperparameters. And they're positive as well for this thing to be proper. So it's a positive distribution. And you can look at Wiki or look anywhere. I assume you've touched gamma distributions at least once in your life. Maybe some problem they came up in. You know, but they can look like this. Positive stuff. And then they can go over here, be heavily skewed. So they're kind of these skewed things. They have positive mass. Turns out, if you have a lot of data in something, they start to concentrate and they look more and more normal. You'll notice that from our old data example, that those posterior distributions, while we didn't say much about it, they started to look more and more normal, more symmetric. They started off totally unsymmetric, the prior. Then it became like something else, and then it started to look bell-shaped, and it got more and more Gaussian looking. In fact, it is looking more and more like a Gaussian. You'll never change anything about the bounds of support, that it'll never actually be Gaussian, but it starts to look very Gaussian. So you see this auto central limit theorem thing kicking in. One of the things you can notice from that analysis is some of the xi's was popping up. The sum in central limit theorem has something to do with sums. Same thing will happen here. So now we haven't discussed using gammas as a modeling tool per se. We're just using it because of its conjugate form. So it feels a little bit more arbitrary. But just as an aside, there's other ways to think about gammas. Or at least connections you could make. So I've made this statement that gammas have something to do with chi-squareds. So chi-squared distribution, there's this other parameter called the degrees of freedom. That's equal to a gamma. Does anybody know? There's twos, yeah, exactly. What happens, so there's two parameters underlying a gamma. So this has a nu in here. By 2, yes. Half, good job. So in the book, if you look at this, it would be a 2 right there. So if you look in Casella and Berger, but that's when they have everything on the other scale when they divide by the betas. And that's totally arbitrary. You nailed it. So what are other ways to think about chi-squareds with new degrees of freedom? What's that? Sums of normals. So maybe sums of zi's where the z's are normal 0, 1s. I goes from 1 to nu. That's chi-squared. Squared. That comes up sometimes. Other ways to think about gammas is the sum of new exponential random variables. You can think about that, and if you study Poisson processes, you would use that to model waiting times, memoryless waiting times. So lots of cool things to think about with these distributions, and there's more to it than what I'm saying, and hopefully I can fill in some of those gaps as we go. Right now, we're just thinking about it as a conjugate prior. Okay, so we can see that it's conjugate. So let's just write that down and finish the analysis. So pi phi, this is kind of the automated part of being a Bayesian, is once you've got your prior, you've established what you want to use and maybe why you want to use it, it's likelihood times prior and recognizing everything. Of course, in high E space, that's not so easy. We don't need to use computers. But this is going to look like phi to the 1/2 e. This is going to be minus phi over 2 x1 minus mu squared. And then we're going to have our prior. And I'll just point out all of this right here is normalizing constant. Remember it. So we will use it in a moment. But for right now, since we're writing everything up to proportionality, we can forget about it temporarily. But I will tell you that normalizing constant is something we use all the time in this class. So I'm going to use the kernel of the distribution, and I'll substitute the z's for phis because I'm placing the distribution on phi. So this will look like this: phi to the alpha minus 1, e to the minus beta phi. So that's our prior. And that's our likelihood. Together, they look like the posterior. At least describes the shape. And everything else just normalizes everything so that it integrates to 1. Just a quick couple points. Does anybody know what the expectation of z is? I'm going to suppress the alpha and beta, but it will be defined in terms of that. Alpha over beta. I would check real quickly if these things were positive. Does that mean that's positive, that it lives in the right space? It does, so at least the sanity check is cleared. So what's the variance? Alpha over beta squared. So again, Every distribution we touch, know these sort of things. It's not a hard exercise. If you want to know how I do it, and I know a lot of people will laugh at this, is I would write a note and put it on my refrigerator. And every time I went to my refrigerator, which is a lot, you know, every time I need water, I go to my refrigerator. I study the note. So if I want to memorize something which is horribly painful for me, I just build it into my day. I take 0 extra time to do it. About a second. And eventually, everything becomes commonplace. So that's what I would recommend. You can also work through these and try to work out the expectation by hand. How do you do it? So I need to multiply this by z, multiply that in there. You have to do iterative parts over and over and over again, and you'd have to imagine alpha was an integer to do it. And then you'd come up with some weird notation if alpha wasn't an integer. You'd start to discover what a gamma function is. Okay. We're going to combine like terms. So this is going to be alpha plus 1/2 minus 1. So I've just combined this and that. E to the minus phi. And I've got x1 minus mu squared over 2 plus beta. So I've combined the terms. Where do I look for the terms that describe which gamma this is? Right there and right there. So gamma distribution, all I have to do to recognize it is look at the linear leading, or whatever this term is that's exponentiated. Remember, there's always a minus 1 out in front of it. So if that minus 1 isn't there, you'll have to add 1 and subtract 1 to recognize it. But it's always sitting there. Where do I recognize the other term? It's always in the exponential term. So all things you just need to know. It'll keep you from solving integrals that you really can't solve anything. So this is a gamma with parameters alpha plus 1/2 and x1 minus mu squared over 2 plus beta. Let's do a sanity check to see if this answer makes any sense to us. I can't think about a lot of parameters. I kind of know that, you know, the second moment has something to do with diffusion. I know that the third moment has something to do with the kurtosis of everything and the skewness of everything, so on and so forth. But I can at least think about the mean because it at least lives in the same space I'm used to thinking about. So I can kind of think about the mean. So I like to calculate the mean and see, does that make any sense? So, and if it doesn't, then I probably want to look for my error. So the expectation of phi given x1 mu, I'll be polite and write down all the conditioning. This is going to be equal to this thing over that thing. So alpha plus 1/2 over x1 minus mu squared over 2 plus beta. We have to ask, does this make sense? So let me just ask you an aside question. So one more aside. If somebody came into you, say you're sitting at your desk, laboring over something highly theoretical, somebody sees that you're the one to ask, and says, I have this one data point that came from a normal distribution. I know that it's normal. Don't ask me how I know. But I know. If somebody had one data point and said that it was normally distributed, I would probably stop the analysis. But let's just imagine. So they say, they got it. And they said, I know what mu is. That's cool. Very convenient. They also know what mu is. So I guess if they know it's normal, then I guess letting them know what mu is okay too. But I don't know what the variance is. Please tell me a good estimator of variance. If you knew what the mean was in a distribution and you had a collection of data points, how would you estimate the variance? Yeah, sample variance. So what is that? That's like sum xi minus, you would choose, some people would use x bar, but some people have mu in hand, so they would prefer to use that. X bar is measuring mu, it's estimating that, so I'd rather use that, square it out, divide by n. This is at least the unbiased choice to divide by n. Oftentimes people will do this if they don't know what that is, and they'll use the unbiased estimator. I will point out, I always do that. So even when I use x bar, this is closer on average than the other one. It's biased, but it has less variability. Saying that, if n is even moderately large, and this is what we're quibbling about, we've got really big problems. So you'd probably do that. Divide by n. This is the unbiased estimator. Seems pretty good. We'd all agree on it. We only have n is equal to 1 data point. So we'll replace that with 1. We'll replace that with 1. So this is what you might think is a sane answer. At least appealing to our classical rationale. Eventually I'll stop doing that and let Bayes speak for itself, but right now it's good to see things kind of align. This is not quite that answer. It's flipped over. It has some regularization in here, but it's flipped over. At least it kind of has that term in there, and it's inverted. Why is it inverted? Because I'm talking about phi here, where this is an estimate of sigma squared. And they're inverted. They're inversely proportional to each other. They're inverses of each other. Okay, let's go back to the other analysis. So the prior that we used, and I'm going to suppress the hyperparameter notation. Usually you don't see it, but I like to tell people about the hyperparameters. I want them to ask why I picked them. I'll always have good reason. So if anybody ever hides them from you and says that it doesn't really matter, be skeptical. Unless you really know everything about what they've done and you've done it before. So this looks like this. Phi to the alpha minus 1, e to the minus beta phi. And recall, pi phi proportional to 1 over phi is scale invariant. So that kind of looks like this if I have certain choices of alpha and beta. So this, with alpha is equal to beta is equal to 0, is going to be equal to 1 over phi. So this prior right here, the scale invariant prior, is a limit of the conjugate prior. And I'm going to give you other good reasons for really liking this prior, but I'll tell you one more. Laplace used this, and it fascinates me why. He never said. Did an analysis. It's one of those in the margin sort of things. So Laplace used that prior too. So everybody knew stuff about normal distributions back in the day. Kind of interesting. So anyway, this prior that we motivated was a limit of the conjugate prior, and that was true in for the flat prior too. The limit was, as we approached infinity, the other side of things, but it was still a limit of the conjugate prior. So what I could do is I could substitute alpha and beta for 0 right there if I wanted to use this scale invariant prior. I want to point out alpha and beta are supposed to be strictly positive for the distribution, and that makes it so that it's a proper distribution. It integrates to 1, or it integrates to something finite, and I can find the integrating constant. No matter what I do right here, 1 over phi is not integratable. So that was the big thing we learned in calculus. Even though it's decaying in the tail, it's not decaying fast enough, and it sums to infinity. So prior's not proper, but the posterior distribution, if we end up using this limit, so if we use pi phi proportional to 1 over phi, then our expectation this just relates to alpha and beta is equal to 0 in the conjugate prior. Our expectation on phi, given x1 in mu, is going to be equal to 1/2 over x1 minus mu squared over 2. And that's kind of nice. Those halves cancel. And I'm left with 1 over x1 minus mu squared. I don't know about you, but these sort of things make me feel comfortable. Like, oh, there's an alignment between different ways of thinking. And maybe I've got some knobs that I can turn and figure out how much I want that to overlap, or maybe I have these knobs and I can do something with them, inject other information that I know from somewhere else. I think best of both worlds. So anyway, that's our answer for this problem. And I think it kind of makes sense. So again, we're just kind of studying the mechanics of being a Bayesian. Let's do one more problem in our last 8 minutes. Let's figure out what this is, our margin. So what this distribution is supposed to describe is your inference on mu, given that you don't know what sigma squared is. So you got to be careful when you read the literature. If they describe that, they might say, oh, sigma squared's a known constant, so I didn't write it in. So you need to familiarize yourself with what their notation is. What I'm trying to describe is there's no sigma squared in here. So quick question. What, in Stat 101, if you don't know sigma squared, i.e. you estimate it with s squared, what distribution do you base your inferences off of? T. Yeah, exactly. So let me just write down what a t-disk is. So recall, we won't get here until next time, but a t-disk looks like this. So I'll just use my dummy notation for the random variable. It has 3 parameters in there. This is the scale. That's the location. And this is the degrees of freedom. Now, I'd like to spend more time talking about this distribution next time, but I want to just write it down. Sigma's outside. Minus mu squared over nu sigma squared raised to the minus, does anybody know? Close.
Mu plus 1.
I say nu, but it doesn't look like a v, doesn't it? It's fine. So, totally arbitrary. Yeah, nu plus 1 divided by 2. So this is the kernel. We will never use the normalizing constant for anything. There's only one reason I know it, and it's because I teach. So I've never used it for anything. I could imagine if you were doing Bayesian inference on the degree of freedom, you would need that, obviously. And I've seen it done before. I've just never done it. This is what a t looks like. We'll remember that. So possibly this has something to do with the t distribution. So let's just do the analysis. How do we get this distribution given everything we have? There's only one gig in town. What we would need to do is find the joint distribution. I like phi, so I'm going to stick with that. So I need the joint distribution. I need to marginalize out phi. So this is just probability theory 101, where I'm going to integrate over the whole world of phi lives between 0 and infinity. And so you take, to get margins, we marginalize, i.e. we're averaging over phi. Keep in mind this is probability density, and by adding things up through a probability distribution, we're effectively averaging. So This is the marginal distribution. It represents what you would want to say about mu, given you didn't have phi in the first place. So what does a Bayesian need to do to get this? They need a joint prior on mu and phi. I'm going to address this much more clearly next time. But let's just say, and I don't want to be super cavalier about this, so I do want to spend my typical 10 minutes talking about this. About joint priors, what it means. But let's just take the priors we had. Okay, I just want to do as an exercise. Use pi mu proportional to 1. We liked that before. Let's use pi phi proportional to 1 over phi. Again, I think we liked that before. At least it had some appeal to us. So let's use those. And so what I'm going to do is I'm going to use the joint priors, just the product of those two things. So a priori, I don't know the relationship between those two things. And I do think that makes sense. There are other reasons where you could form relationships between the parameters. We can talk about that later. It's not common. So what I need to do to get this is I'm going to integrate over the likelihood times my priors. So I'm going to make this proportional. I haven't normalized it all, but I'm going to do the same thing, and I'm going to try to recognize the resulting distribution and then figure out what its parameters are. Probably has something to do with a t. So knowing what a t looks like is kind of critical. So I'll just do this integration. If this is fast, that's okay. I'll come back next time and start with this. E to the minus phi, x1 minus mu squared. There's a divide by 2 there. And then I'm going to have my 1 times 1 over phi. So likelihood times my priors. That's phi inverse. You'll forgive me for doing that. We'll come back and write it down slower next time. And then I just need to integrate this thing. How do I do it? Iterative parts. If alpha, or that thing, that's a half, so I'm going to have to start thinking about gamma functions in a second. Easier thing to do is to recognize this is a gamma. Which gamma is it? It's a gamma 1/2 with this parameter, x1 minus mu squared divided by 2. If this was normalized, it would integrate to 1. So if I was multiplying by that thing that I had before, beta, that's the normalizer. If I had that thing in here, which I don't, it would integrate to 1 because it's a distribution. I used to prove that in class. And you can go back to some videos if you want to see it, but it's in every standard probability book. So this is going to, and I just want to tell you, my notation for this is that's alpha tilde and that's beta tilde. So I should have had tildes in there. So this thing is going to integrate to the inverse of the normalizing constant for a gamma distribution. And the only way I can do that is to know what a gamma looks like. We'll come back, we'll do it slower next time. But I can write down what this is. This is a constant, that's just a gamma half. Does anybody know what the gamma function of a half is? Yeah, it's crazy. Super cool. Square root of pi. So this thing right here, x1 minus mu squared. I can divide by 2. I don't really need it. It's all proportional to this, is our answer. So, and I'm going to take this to the half power. That's a constant, that's a constant. We are writing everything down up to proportionality in the first place. So everything's written up to proportionality. So I'm going to simplify that and say that's proportional to x1 minus mu. That's absolute value. I have that squared and then square root. Positive number, square root, absolute value. So this is what we are after. Our posterior on mu, we think it looks like that. So this is its algebraic form. Any problems? What distribution is that? Maybe a t. So let me ask you a question. Is it proper? So remember where mu is going to live. So integral 1 over x1 minus mu absolute value d mu between negative infinity and infinity. What is that? Try to integrate 1 over x.
Yeah.
In the positive range. What did they tell you that does? It diverges. For the same reason, 1 over something. This is just shifted around x1. So this is improper. You might think, well, it kind of has a peak around x1. That kind of makes sense. Tails come down. But the fact that the tails don't add to something finite is a big problem. And that's how we do our uncertainty, is all the actions in the tails. So I always think that the distribution is the important thing, not the expectation per se. How do we come up with our bands of uncertainty? That's the big deal. And so there are no 95% bands. There's an infinite amount of mass under those tails. And so that's improper. So let's come back next time and have a quick discussion about what should we do about it. There's a couple different choices. Anybody want to prescribe something? What would you do? Use different priors. So maybe make conjugate priors and inject some mass. Anybody else?
Sample from it anyways.
Do it any way you can. You would bound it or something like that, chop off the tails at some point?
Yeah, and then just divide by the total mass that you have.
So you can't divide by it unless you like truncate it.
Yeah, do that.
Okay. Sam's going to say he knows something about ranges for mu and chop it off. Cool. What about other people? So Sam just said something that he's going to come up with a prior that truncates things out. That's the way I would interpret it. And Perul said she's going to come up with proper priors. I'll give you a theorem next time that says if your priors are proper, posteriors will be proper. So at least we have a proper prior, or a proper posterior. Anybody else have a prescription? Let me make one comment. You're trying to effectively infer the variance and the mean from one data point. You needed a joint distribution. I wouldn't, like if somebody came in with one data point and wanted me to say things about variation, the only things I can say about it are things that I've presupposed. So all your info would come from the prior in that case. And I don't like that analysis. So I like Anna's answer, go get another data point, but while you're at it, get a few more. Let's come back and talk about that next time. Thanks you guys. Sorry for going over. I promise to give you the time back eventually.